So I should mention to you that in the previous lecture when I was talking about the application of magnetic field, I was looking at a system of free electrons where there was no collisions. So that is the reason why I did not have the minus p by tau term. So if you look at it here, I don't have a damping term which is the p by tau, but I only have the force term, and that is only the force term is what I have here and no damping term. And what I am going to be doing now is look at electrons actually in a metal and study what happens when both electric and magnetic fields are present. And the configuration in which I am going to be looking at is the following. I will have a sample, and in this sample I have a current that is flowing which is J of x, and because of the current flow you must have an electric field present which is E of x, and then I apply a magnetic field which is perpendicular to the direction of the to the plane of the sample. So because of that what happens is I have a force. So when the current is flowing in the from left to right, the velocity of the electrons is in this direction, V of x, and when I apply a magnetic field in the z direction which is h here, then I will be having force in the perpendicular direction which is minus EV cross h, and this what it implies is that the electrons will move to the bottom part which is minus minus minus, and leaving the bottom edge in this diagram charged negatively. So the top edge is charged positively. So what is happening is the electrons kind of bend around in this way because of the magnetic field. So in this configuration what I can write down is the equation of motion for the electrons. So what we have is dp by dt is equal to minus p by tau plus f of t, and f of t is actually due to both an electric field and a magnetic field, which is given by E by C V cross H minus E times E. So substituting this, what I will get is the following equations, almost similar to what I got last time, except that I have a p by tau term. So I will have dpz by dt is equal to 0, dpx by dt is equal to minus Ex minus px by t by tau rather minus omega c py, and dpy by dt is equal to minus Eey minus py by tau plus omega cpx. So given this, what we will do is we will look at the steady state. In the steady state there is no current flowing in the y direction, and what we have is dpy by dt is equal to 0, and we will get in the steady state dpy by dt is equal to 0 and dpx by dt is also equal to 0. So I have a steady current, so the dpx by dt will be 0, but the current is constant. So we can write down in this case we can write down EEX minus EEX. There is no, sorry, once I write the components there is no arrow on top. Minus EEX is equal to omega C Py plus Px by tau, and minus EEY is equal to minus omega C Px plus Py by tau. If these equations are multiplied by minus Ne tau by m, so multiply the equations by minus Ne tau by m, what we would get is Ne squared tau by m Ex is equal to omega C times tau, because Py is I mean you can do the algebra, it's quite straightforward. Omega C tau times Jy plus Jx, because you know that Py is related to the current, and so you can always write down Py by m will be the minus E Py by m will be the current. And similarly Ne squared tau by m Ey is equal to minus omega C tau Jx plus Jy, or I can write down sigma naught or sigma naught Ex is equal to omega C tau Jy plus Jx, and sigma naught Ey is equal to minus omega C tau Jx plus Jy. If there is no current flowing in the y direction, so let us look at the steady state. In the steady state, when Jy is equal to 0, that is no current is flowing except in the x direction, then what happens is that we can write down sigma naught Ey is equal to minus omega C tau Jx, or Ey is equal to minus omega C tau by sigma naught times Jx, and substituting for omega C and the sigma naught, we will get minus Eh by mc tau divided by Ne squared tau by m, and this will give me minus 1 upon NEC into h times Jx. So what we have is the electric field that is developed along the y direction is actually proportional to the magnetic field and the current that you are passing. So if we can define a constant which is called the Hall constant RH as equal to the electric field in the y direction per unit of magnetic field and along the z direction, and unit current along the x direction, then that is known as a Hall coefficient, and we see that the Hall coefficient is given by minus NEC. So RH is small for metals where n is large, the number of carriers is large, so usually it is small, and sign of RH or the sign of the electric field depends upon the charge of the carriers, upon the sign of the charge of the carriers, sign of the charge of the carriers. So, we see that RH should be negative for electrons and positive for charge carriers, which are charge carriers whose charge is positive. We will come across those in a while. Okay. So, by measuring the Hall coefficient, you will be able to actually get the sign of the charge carriers as well as the number of charge carriers. Of course, in this case c is the velocity of light, so that is a constant. One of the great things about Hall effect measurements is that it was first done in metals where the Hall coefficient is very small. So, it was a really classic measurement in the sense that it was rather difficult to measure the voltages that were developed perpendicular to the direction of the current, but nonetheless it was a classic experiment which was done almost over 100 years back. And what happens when we also have a non-steady state conditions? When the conditions, incidentally I should also say that when we are looking at the Seebeck coefficients, the sign of the Seebeck coefficient also depends upon the sign of the charge carriers. So, it is positive for positive charge carriers and negative for negative charge carriers. And if the conditions do not correspond to a steady state, then we have Jy is non-zero. So, when Jy is non-zero, then what is the direction of the current? Relative to the electric field. So, we must remember that the electric field now has both Ex and Ey components, and then we have to find out what is the direction of the current. So, this can be done quite simply because you can just calculate E cross J by E dot J. So, that will give me a tan phi, where phi is the angle between E and J, and using these equations that I have here, using these two equations that I have here, I can actually calculate this quantity, and what do we get? Phi we will get as equal to omega c tau. Tan phi is equal to omega c tau. So, you see that we can also know the direction of the current, and phi is known as a Hall angle. Now, measurement of Hall effect showed that the Hall coefficient R in real cases depends upon the magnetic field. Strength. So you can have R changing with the magnetic field, and in fact and R saturates at high magnetic fields, high in terms of the magnetic field being about 1 Tesla. So it saturates. So, but there were some very interesting and very surprising aspects of this. In metals like aluminum, high field RH was positive, which meant that the charge carriers were actually positively charged in the case of a metal like aluminum, and it is very difficult to know why it should be positively charged. Okay, because all of them, because first of all, aluminum contains electrons which are actually moving around. If electrons are moving around, you would expect that the charge carriers are electrons, and so the sign of the Hall coefficient should always be negative. And it was also not known why the Hall coefficient should depend upon the magnetic field. So while using the Drude's theory, one could get quantities such as, Drude's theory, we could get quantities such as sigma, q, the Seebeck coefficient, and then we also could get the coefficient which is actually the thermoelectric power. So Q is the thermoelectric power. And we could also get the thermal conductivity kappa, and we could get something like the Hall coefficient R, the dielectric constant epsilon as a function of omega. So many of these things could be calculated. Okay, although many of these things could be calculated, the question was, there were many inconsistencies. First of all, the problems were the specific heat. We could also calculate the specific heat, okay, and the problems were that the specific heat was far smaller, rather was far larger. Okay, it was than what is found for metals. The success, which was that the Lorentz number being reproduced, was because of cancellation of errors. CV about 100 times larger, and V squared about 100 times smaller. Than in real metals, in real situations. And of course, another problem was the Hall coefficient was dependent on magnetic field, and sign could also be positive at large h. So many of these problems were troubling, and of course the Drude's theory was basically a classical theory. What we did was completely classical, and in the classical theory this is the best that we could do. So one had to go beyond classical theories, and of course when Drude came up with his theory, then quantum mechanics was not known. So quantum mechanics was sometime in 1900 when Planck introduced his quantum law, and then you came up with the model of the atom, which was the Rutherford model, and then the Bohr's theory of the hydrogen atom was in 1913, and of course quantization of the photons was in 1905, which was explained in 1905 by Einstein. So what Sommerfeld did was to use quantum description of the free electrons to get properties of metals. So when we talk about free electrons, the Hamiltonian of the free electrons is the following. Hamiltonian for the free electrons is just minus p squared by 2m equal to minus h cross squared by 2m del squared, and the eigenvalues are minus h cross or plus h cross squared k squared by 2m, and eigenfunctions are e to the power I over ik dot r. Okay, so you can think of the free electron picture as being obtained from electrons in a box of very large size. So you can actually think of a potential a box like a particle in a box. If the particle in a box in one dimension is, if the length of the box is very very large, then you can think of it as a free electron. So that's one way of approaching it, and another way of approaching it is assuming that the electrons are indeed free and there is no potential. But because we are dealing with metals which are having finite dimensions, it makes sense to deal with the box which has the size of the dimensions of the metal. So if it has the size of the dimensions of the metal, then the k values, the allowed k values correspond to the allowed standing waves. Which means that are allowed are ones which have which are single valued when, or functions which are single valued when we make a translation equal to the length of the box. Length of the box in each dimension. So what we are actually doing is the following. We have a box of length Lx in one dimension, Ly, Lz. So which means that I can think of it as a box which is, if this is the x direction, then it is a circle of length Lx of circumference Lx or Ly or Lz. So if we did that, then if I am looking at the wave function as e to the power I kx times x plus ky times y plus kz times z, then if I go to if it is psi of x comma y comma z is equal to this one, then if I go to psi of x plus l lx comma y comma z, then this is equal to e to the power I kx lx times e to the power I kx x plus ky y plus kz z, and this should be equal to psi of x comma y comma z because of single valuedness. So what it implies is that I must have kx lx is equal to 2 pi times an integer, nx, let us say nx is an integer, I can use the same boundary conditions in the y direction and in the z direction, in which case I will get ky ly is equal to 2 pi times ny ky kz lz is equal to 2 pi times nz ny integer and z integer, and so kx can take values 2nx pi divided by lx, ky can take values 2 ny pi by ly, and kz can take values 2 nz pi by lz, and nx ny nz can take values 0 plus minus 1 plus minus 2 etc. etc. So this is important, and the energies are of course given by h cross squared kx squared plus ky squared plus kz squared by 2m. Now what is the difference between the classical theory and the quantum theory? One, apart from the fact that the energies are given by this, which are actually more or less the same. If you are looking at an infinite system, it is the same as the classical theory, the quantum energies. But the important thing is that every state k given by x times kx plus y times ky plus z times kz can have at most 2 electrons, each of opposite spin, each of ms equal to plus half or minus half. Can have at most 2 electrons of ms equal to plus half and minus half. Actually, if it is 2 electrons, then it is plus half and minus half. So what we are saying is that if I am looking at it in the one dimensional picture, and if I try to plot E as a function of k, it is a parabola, and you will have energy levels which are given by different values of k. So here you can at most have each level that I am looking at can be either 0, 1 or 2 is occupancy. Similarly 0, 1 or 2, occupancy is 0, 1 or 2, 0, 1 or 2, and it can never exceed that. Okay. So, and how is it actually described? It is described by a Fermi-Dirac distribution. That is, whether a state F, whether a state is occupied or not, depends upon, if I look at a state epsilon, or a state of energy epsilon, then whether it is occupied or not is given by the probability of occupation of that state is given by F equal to 1 upon e to the power epsilon minus some constant epsilon f times beta plus 1. Beta is equal to kBt, and epsilon f is a chemical potential. So, what you will see is that when beta is equal to 1 upon kBt, sorry. Okay. So, what one sees is the following, that is, when the temperature, when T goes to 0, then F is equal to 1 for all energies E less than epsilon f, and equal to 0 for all energies E greater than epsilon f. Okay, so we will take it on from here. I will say a little more about the Fermi-Dirac distribution function and contrast that with the Maxwell-Boltzmann distribution function, which is a classical distribution function, and I will also derive all the properties using the Fermi-Dirac distribution function, the properties of the free electrons, which is a quantum free electron gas, and that is a Sommerfeld theory. And we will also discuss how Sommerfeld theory corrects some things related to the properties of metals, but fails to explain a few others, and how one has to go beyond the free electron approximation in order to obtain properties of real metals. Thank you. We will start again tomorrow. Bye.